In this video, we're going to conduct a simulation-based test to compare two means, as is done in our Introduction to Statistical Investigations curriculum. Many students pull all-nighters when they have an important exam or a pressing assignment. But can you really function well the next day after a sleepless night? What about a couple of days later? Can you recover from a sleepless night by getting a full night's sleep on the following nights? This last question, about the lingering or delayed effects of sleep deprivation, is what researchers Strickel, James, and Hobson investigated. They published their results in Neuroscience in 2000. They had 21 volunteer subjects, ages 18 to 25, that were shown either screen A or screen B for 17 milliseconds, then a blank screen for various lengths of time, then they were shown screen C for 17 milliseconds. Note the array of diagonals and an upside-down T and an L on a slant in screens A and B. The minimum time of the blank screen was recorded where they achieved 80% accuracy in describing whether or not they saw a T or an L and a horizontal or vertical array of diagonals in the first screen they saw. That minimum amount of time of the blank screen was the subject's score. After this, the subjects were randomly assigned to one of two groups. One group was deprived of sleep for 30 hours, followed by 2 full nights of unrestricted sleep. The other group was allowed to get unrestricted sleep on all 3 nights. Following this, both groups were retested on the task to see how well they remembered the training from the first day. Researchers recorded the improvement in the scores as the decrease in time required at retest compared to training. Note, positive numbers mean they improved their task. In other words, they performed the task faster. The goal of the study was to see whether the improvement scores tended to be higher for the unrestricted sleep treatment than for the sleep deprivation treatment. So our null hypothesis is that there is no association between being sleep deprived or not and the improvement score, or that the improvement score is not affected by being sleep deprived. The alternative hypothesis is that those with unrestricted sleep will have higher improvement scores on average than those who are sleep deprived. In other words, the improvement score is affected by being sleep deprived. We will let mu unrestricted be the long-run mean improvement on this task 3 days later when someone has had unrestricted sleep, and let mu deprived denote the long-run mean improvement when someone is sleep deprived for the first night. We can then write our hypotheses in symbols like this. Here are the results. The sleep-deprived group's improvement scores are on the top dot plot, and the unrestricted group scores are on the lower. We can see with these dot plots and the means below them that the unrestricted group improved much more than the sleep-deprived group. Our statistic is the observed difference in the average improvement scores, or 15.92 milliseconds. There are 2 possible explanations why our mean improvement scores were so far apart, or our statistic of the difference in the scores was so large. The first is that there's a tendency to improve more if one is given unrestricted sleep. This is the alternative hypothesis. The other explanation is that the improvement scores are not affected by sleep, and many of those that were going to improve more were assigned to the unrestricted group just by chance. This represents the null hypothesis. We want to set up our simulation to reflect this null hypothesis. In other words, the improvement scores have no association with the groups to which the subjects were assigned. They were going to improve by those numbers no matter if they were sleep deprived or not. Hence, we can randomly assign the subjects' improvement scores to one of the 2 groups and calculate a difference in the 2 means to find out what sort of results we would get just by chance. We will do this with index cards. We can write all the 21 times on 21 cards. Then we'll shuffle those 21 cards and randomly distribute them into 2 stacks. One with 10 cards, representing the improvement scores of the unrestricted sleep group, and another with 11 cards, representing the improvement scores of the sleep-deprived group. Note that we are using the same sample sizes as the original experiment. The shuffling, again, assumes the null hypothesis of no association between sleep deprivation and improvement scores. After shuffling, we will calculate the difference in the average scores between the two stacks of cards. And then we'll repeat this many times to develop a null distribution. Let's try this out. Here are cards representing the results from the actual study, with 10 blue cards representing the improvement times for those in the unrestricted group, and 11 red cards representing the improvement times for those in the sleep-deprived group. We shuffle the cards and deal them into our piles of 10 and 11. In doing so, just by chance, the unrestricted group mean improvement time is 6.38 and the sleep-deprived mean time is 16.12. This gives us a difference in means of a negative 9.74, and this becomes the first dot in our dot plot of could have been values. Let's repeat this process. This time, the unrestricted group mean improvement time is 12.7 and the sleep-deprived mean time is 10.37. This gives us a difference in means of 2.33, and this becomes the second dot of simulated differences in means in our distribution. Let's repeat this process one more time. This time, the unrestricted group mean time is 14.12 and the sleep-deprived mean time is 9.08, for a difference in means of 5.04, which becomes the third dot in our null distribution. Note that none of these simulated results are as extreme as the actual observed difference of 15.92, so it's starting to look like this observed difference might be unlikely to occur just by chance. But we need more than just 3 simulated results. In class, I would have each of my students shuffle the cards and compute a difference in means. They would then plot those differences on the board, and the results might look something like this. In this class of 30 students, we find that none of our simulated results are as large or larger than that of the actual observed statistic from the study. Hence, at this point, my p-value is 0. To get a better idea as to what our p-value is, we should really do more repetitions than just 30. To do this, let's use our multiple means applet. In this applet, we start with our dot plots and improvement times with the sleep-deprived group on top in red and the unrestricted sleep group on the bottom in black. When I click on the shuffle responses, the dots or the improvement times get shuffled and then randomly distributed into the two groups, just like we did with the cards earlier. In doing so, we get a difference in means of a negative 1.76, and that number is used to start our null distribution. Shuffling again, we get a difference in means of 2.58, and that number is added to our null distribution. Now let's take full advantage of the power of the applet by shuffling the improvement times 998 more times for a total of 1,000 repetitions to see what the results would look like in the long run under the assumption of no association. Note that the mean of the null distribution is approximately 0, which is what we would expect because it represents the simulated outcomes when there is no underlying difference in the improvement scores between whether or not someone is sleep deprived. Thus, we would expect our difference in sample means generated under this true null to reflect that and cluster around 0. And we can also see that the observed statistic of 15.92 is way out in the tail of the null distribution. This shows that even though it's possible that the random assignment process alone could lead to such a large difference between the two groups, it's quite unlikely. In the 1,000 shuffles, there were only 5 of the simulated results with a difference of 15.92 or higher, so our estimated p-value is 5 out of 1,000, or 0.005. What does this p-value mean? It means if sleep deprivation had no effect on improvement scores, and we randomly assign 11 scores to the sleep-deprived group and 10 scores to the unrestricted group, a difference of 15.92 milliseconds or more would occur in only about 5 out of the 1,000 repetitions. Therefore, we have strong evidence that sleep deprivation will reduce the improvement scores. Since this was a randomized experiment, we can determine that sleep deprivation that occurred was the cause of the lower improvement scores. Note that we could easily have done this test comparing medians or any other statistic we would choose. The process would have been the same except for the choice of statistic. Let's summarize what we have done using our 3S strategy. We first computed the statistic from our sample. In this case, it was the observed difference in means of 15.92 milliseconds. Then we identified a chance model that reflects the null hypothesis. We used cards representing the improvement scores and randomly distributed them into two groups, sleep-deprived and unrestricted sleep. Then we computed the difference in means. And finally, we repeated this process 1,000 times to develop a null distribution. Then we found that the observed mean difference of 15.92 is way out in the tail of the null distribution, and only 5 out of 1,000 repetitions were as large or larger than 15.92. Thus, our p-value was 0.005, and this gave us strong evidence against the null.